We are at 345 megahertz. I forget where they draw the line for UHF.
Okay, thanks.
Yeah.
And we were talking about like the lost electrons, so those are just ones going through the atmosphere that weren't being reflected back.
Yeah. Let me bring up that slide again because I realize. Yeah, so the particles, typically they mirror outside of Earth's atmosphere. And then they can bounce back and forth, and then they also do a drift around the Earth, and that's how you get that toroidal donut shape for the outer belt. But if they have the right components in their velocity that they mirror in Earth's atmosphere, then they collide with neutrons. That process generates the aurora. So when you see aurora, what you're really seeing are energetic electrons colliding with Earth's atmosphere. And then they're lost from the system because they're now very low energy particles in Earth's atmosphere after the collisions. Does that answer your question?
So you said that like your first NSF proposal was rejected. Do you know why?
Yes. So I came in once the funding began, but I was told why that was rejected. And it was because we had overscaled the mission. We had designed it to have both a particle sensor and then also a solar imager. And the reviews came back such that they didn't think you could do 2 science instruments of that scale on a 3U CubeSat. So before we proposed the second time, we de-scoped the entire mission, decided to keep the particle telescope. And that gave us more mass and more volume and more power to run everything else.
Is there a concern about all of these CubeSats in orbit? You know, might hit other things? Are they designed to eventually go out of orbit?
That's a good question. So NASA, when you launch, I'm actually not sure if it's NASA or international, but NASA's the one who regulates it. And they mandate that you have to prove that whatever you launch into outer space will deorbit within 25 years. So you can do that passively from a low Earth orbit like ours. It will naturally decay in about 19 years. That CubeSat that I showed earlier that had all of the different sprites that got ejected, that was in a much lower orbit, and that actually decayed and burnt up in the atmosphere before they could eject all of their little mini satellites, which was a huge bummer. You can also deorbit your satellite actively, like with a solar sail as like a big parachute and stuff like that. Or just do a burn, like put propulsion on your spacecraft, so that way we'll deorbit actively. On a similar note, you also have to prove that your spacecraft, when it deorbits, won't land on anybody. So you have to buy insurance against the fact that your spacecraft might kill somebody somehow. You have to prove that you have like less than a 1 in 10,000 chance of hitting a populated area after it deorbits.
So do you do that with like materials engineering? Like do you select your materials and hope that like 99% of it burns up as it comes down?
Yeah, so we didn't have to actively do that. It turns out the materials we chose already satisfy that requirement. But if you didn't satisfy that requirement, you'd have to go back and redesign, make sure you have lower density materials that will burn.
Yeah, isn't it harder to design something that survives the atmosphere?
Yeah, the atmosphere is really good at burning up.
So, is it possible to launch satellites using, the like rocket model instead of mission or NASA giant rockets?
You mean from a rocket? Or just as a secondary payload?
No, I mean I launch from the Earth.
You mean without going through NASA?
Yeah, because you're talking about like increase the accessibility of to all the people of these cities. So if it's just constrained to NASA's capability or SpaceX capability, it's still limited.
Yes, going to outer space is very expensive. The nice thing about the NASA opportunities is that they'll pay for it as long as it's an educational, there's like educational objectives associated with it. Going to the space station is also expensive. It's not quite as expensive because they ferry a lot more mass up and down. As far as I know, it's really hard to get launches in outer space, period. If you have the money to pay for it yourself, you can put whatever you want up there. But if you don't, you kind of have to rely on these secondary payload sort of opportunities.
Yeah, I had a question about the reliability of the data. Since you are basically sending semiconductors into space, there's plausibility, as you stated, that you can get switch bits or what have you from this giant magnetic field around the Earth. Was there some sort of secondary checker for that? Was it those weather balloons, whatever they were? Like, how reliable is your data?
Is it our data specifically, or like data that comes from?
Data comes from that region of space.
Yeah, so generally because NASA can afford to pump money into these projects, like the big flagship mission ones, that data is very reliable because they have redundant systems and proper shielding to prevent the particles from penetrating. We didn't have the resources to do that. So we actually had a number of these bit flips that occurred. And typically, I actually, in one of these slides, I can show you. This one's better, yeah. So you see this loss of contact right here?
Yeah.
So we lost contact from the CubeSat for about 3 months because we had one of those bit flips. And we didn't know about it until it came back to life and told us that it had a bit flip. So what happened was we don't have redundant systems, we don't have shielding, so something happened to one of our ADCs, and it was a critical ADC, and it ended up temporarily latching up the radio. So the entire CubeSat was working completely nominally. It just couldn't tell us that it was working nominally, and we couldn't tell it, or ask it what was going on. So the radio ended up draining the entire battery. The entire system reboot because the battery went to 0. And then on reboot, the bit flip cleared, and then we were able to talk to it. So yes, we had probably 6 or 7 similar events. This was the only one that hit a critical ADC. We lost a lot of our sensors, ended up going bad because the ADCs are really sensitive to these sorts of radiation, and all of the sensors run on ADCs. So we lost like voltage sensors and temperature sensors. Towards the end of the mission, we had only 10 or 20% of our sensors on board still working.
So with that reboot that happened, was that like an intentional design thing, or just
Yeah, that was an intentional design thing. Some of the mentors at LASP decided that it would be a good idea to include that. They called it Phoenix mode. If something went wrong, it would be able to drain the batteries and then boot back up. So that was a design decision.
Did you use that in a paper? Call it Phoenix mode in a paper?
Yeah. A number of times. We also called it, once it came back, we called it Zombie Sat for a little while.
It looks like it kept operating a lot longer than you guys originally expected. Do you have any hope that it'll come back online? Or?
Yeah, so that's also a good question. The components that we chose to use were non-space rated. And in fact, a lot of them were bought from Amazon. Our batteries were actually remote control car batteries that we kind of rewired to run a spacecraft. And because the mission went on for so much longer than we expected, the batteries were only spec'd to 1,000 cycles or whatever. And because we went on for so much longer, the batteries ended up degrading. And that's why towards the end, you start seeing less and less data, is because we're only power positive for increasingly small periods of time. So normally, what happened in the past is it would go dead, and then we would just wait until it was power positive again, and then it would wake back up and we'd say hi. But the last time we saw it showed that the batteries had degraded a lot. So we don't expect the batteries to recover this time. Still have our fingers crossed.
Can you please let us know, like, which stage of this development process did you have to use clean rooms? The images you showed, I just noticed when you were actually putting the CubeSat in the P-pod, you had the clean room, but any other stage needed that?
That's also a good question. So this was for the instrument. We used a clean room because the sensors we used were high voltage, and if we ended up getting any debris on there, it would end up shorting the system. So we had to make sure that the instrument was clean. But for the rest of the integration, we didn't use a clean room at all.
Can I ask another question about the manpower you had on this team? You mentioned you had several graduate students. I was wondering, did you have also undergraduate students on this project?
We used undergraduate students, but in very small scales. I think the only times we used undergraduate students were in operations, when the CubeSat had a 3 a.m. pass, and nobody wanted to run it. We hired some undergrads to run those passes. So I'd say 98% of the work, 99% of the work was done by graduate students. I think we had 4 PhD students and then 65 master's students that came and went throughout the 4 or 5 years. Turns out students aren't experienced and don't do very good work. So if master's students can't have trouble building hardware, we just didn't trust undergrad students. I'll leave it at that.
I guess the last call for questions? No? I think we'll go ahead and wrap this up. Thank you so much for coming. So you guys welcome to order leftovers there are for food. Grab pizza, please.
And drinks.
And drinks. And drinks.